Students are requested to drop down their names for attendance purpose. We'll be starting in a while. Are requested to drop down your name for attendance purpose. We will be starting in a Okay, so we'll start now. So today we will be dealing with the oxo acids of group 15 basically, right? So oxo acids are the acids that contain oxygen, group 15 element, that is maybe nitrogen and phosphorus and hydrogen, right? Apart from being acids, they also possess oxidizing and reducing properties. That means they can act as acids also, but apart from being acids, they can act as oxidizing agents and reducing agents as well, right? Which makes them important for the chemical processes. Now, first let us come on to the oxo acids of nitrogen. So, nitrogen forms oxo acids such as H2N2O2, that is known as the hyponitrous acid, HNO2 nitrous acid, and HNO3 is the famous nitric acid, right, that you must have used in your labs also. So, in hyponitrous acid, that is H2N2O2, if you see the oxidation number of nitrogen, basically what it will be, +1. Similarly, for nitroxylic acid, it will be H4N2O4. The oxidation state of nitrogen will be +2. For nitrous acid, HNO2 oxidation number is +3. For nitric acid, HNO3, the oxidation state is +5. For oxynitric acid, HNO4, the oxidation number is +5. Hydronitrous acid, H2NO2, the oxidation number is +2. So, the important oxo acids of nitrogen are nitrous acid, nitric acid, and peroxynitric acid also, right. So, these we have to study in details basically. Now, first let's come on to nitric acid. It is a colorless liquid, okay, and laboratory grade nitric acid contains 68% of the HNO3. That means in laboratory that you are having the bottles of nitric acid, it is not 100% nitric acid, but it is 68% of the nitric acid by mass, and it is having the specific gravity of basically 1.504, right. So, what is the basic laboratory method of preparation of nitric acid? In the laboratory, nitric acid is prepared by heating potassium nitrate or sodium nitrate and concentrated H2SO4 in a glass retort. So, what is a glass retort? Basically, it is a flask-like substance, right? Flask-like apparatus rather. So, if you heat NaNO3 plus H2SO4, it will give you NaHSO4 plus HNO3. So, this is how you can basically prepare nitric acid in the lab itself. Now, the commercial method of preparation of nitric acid is the Oswald process. So, in this process, there is a catalytic oxidation of ammonia. So, ammonia on reacting with oxygen from air on the surface of platinum or rhodium will give you NO plus water, right. Now, this nitric oxide that is being formed, then it combines with oxygen to gives NO2. Now, this NO2 combines with water to form HNO3 plus NO. So, commercially you can prepare nitric acid by this particular method. Now, here you can see that the NO can be recycled, right. Here the NO can be recycled and the aqueous HNO3 that is being obtained here can be concentrated. That means its concentration can be increased by distillation method, right, up to 68% by mass, and further concentration to 98% can be achieved by removing water or by basically dehydrating it with concentrated H2SO4. Now, physical and chemical properties of nitric acid. First, you see the structure. The structure is oxygen connected with a hydrogen, and then the nitrogen connected to the oxygen, and two oxygens are here connected to the nitrogen itself, right. So, it is a planar molecule basically. It is a planar molecule. So, structure is very important. You don't need to remember the bond lengths and the bond angles basically, but the structure you need to remember. In aqueous solution, nitric acid behaves as a strong acid, right. So, it donates H plus basically, right. When it donates H plus, H2O will become hydronium ion, that is H2O plus, and you are left with the nitrate ion. So, concentrated nitric acid is a strong oxidizing agent. Why it is acting as an oxidizing agent? See here, if you consider the oxidation state of HNO3, basically it will be +1 plus X minus 6 equals to 0, right. And this will become X minus 5 equals to 0, that is equals to X equals to +5. So, oxidation state of nitrogen here in HNO3 is +5, right. This is the maximum oxidation state that can be exhibited by nitrogen. Now, the possibility is that it can reduce its oxidation state to, let us say, +2, +3, +4 basically, right. So, therefore, it reduces its oxidation state by gaining electron, that means by reducing itself and oxidizing the other species. So, that is why it is known as the strongest oxidizing agent, and it attacks most metals except noble metals such as gold and platinum. Okay. Now, the products of oxidations depend upon the concentration of the acid, right, temperature and the nature of the material that is undergoing oxidation. So, different products upon oxidation are obtained. The factors that affect the product of oxidation are the concentration of the acid, basically that what percent of HNO3 you are taking it 68% or 98% basically, and the temperature at which you are performing the reaction, as well as the nature of the material which is undergoing oxidation. Now, the Armstrong's theory, the metal first displaces nascent hydrogen. Now, what is nascent hydrogen? Basically, hydrogen in elemental form. Hydrogen in elemental form is known as nascent hydrogen from acid, which further reacts with acid to give secondary reactions. So, basically, if a metal reacts with nitric acid, there are two types of reactions that are being taking place, that is the primary reactions and the secondary reactions. In the primary reaction, what is happening here is that metal is displacing the nascent hydrogen. The hydrogen is left here and the metal nitrate is being formed, right. Now, the nitric acid combines with this nascent hydrogen in different ways to produce products like NO2, NO, N2O, N2 and ammonia, right. So, these are the secondary reactions. We will look at the example. See here, for copper, if you see, if you treat it with nitric acid, it will give you copper nitrate plus NO plus H2O. If you treat it with nitric acid, the product will be NO2 here, copper nitrate plus NO2. While dilute form, it was having the product as NO, right. In zinc, if you take dilute HNO3 will give you N2O, while concentrated HNO3 will give you NO2. and metal nitrates are common to all the reactions. Okay. Now, some metals like iron, chromium, nickel, aluminium or cobalt do not dissolve in concentrated nitric acid because they form a passive film over them, right? They, for example, in the, I guess we have done before that aluminium forms a passive film of oxide Al2O3 and it does not further react with atmosphere, right? Similarly, here also some metals form a passive film and of oxide and they do not react with concentrated nitric acid. Now, noble metals like platinum, palladium, osmium, iridium, gold, they do not react with nitric acid, but they react with aqua regia. Now, the composition of aqua regia is very important. It involves 1 volume of concentrated HNO3 and 3 volumes of concentrated HCl. This means what? That you are taking HNO3, that is the nitric acid, and the HCl in 1:3 ratio. Okay, so that is known as basically aqua regia, right? So, HNO3 plus HCl will give you NOCl and 2 nascent chlorine. Nascent chlorine means chlorine in its elemental form basically, right? Now, gold reacts with this nascent chlorine to form auric chloride. Now, this reacts with HCl to form chloroauric acid. So, this is how gold reacts with aqua regia. This is very important. Reactions also you have to remember here. Okay. Now, conc nitric acid also oxidizes non-metals and their compounds. So, here if you see iodine, it is having a oxidation state of 0. But here if you see what is the oxidation state of iodine, that is +5, right. So, it is being oxidized here. As the oxidation number is increasing, it is being oxidized here, while HNO3 if you see the oxidation state of nitrogen here is +5 and here it is +4. That means it is being reduced, right. So, here HNO3 is acting as an oxidizing agent. Similarly, for carbon also, it is having a 0 oxidation state here, +4 oxidation state here. Acid also 0 oxidation state here and here +2 plus X minus 8. That means +6 oxidation state here of sulfur, right. So, with non-metal also nitric acid can behave as an oxidizing agent. These products also you have to remember that iodine will be converted into HiO3, carbon will be converted into CO2, S8 will be converted into H2SO4 and P4 will be converted into H3PO4. Okay. Now, this is very important, that is the brown ring test. Again, basically it is used for the detection of the nitrate ion base, right. So, the familiar brown ring test for nitrates depends upon the ability of Fe2 plus to reduce nitrates to nitric oxide, which reacts with Fe2 plus to form a brown colored complex. Now, here if you see the HNO3, basically the nitrate ion reacts with Fe2 plus, right. So, here the Fe2 plus gets oxidized to Fe3 plus while the nitrogen gets reduced here, right. If you see the oxidation state here, here it is +5 and here it is +2 basically, right. So, it is getting reduced as the oxidation state is getting decreased. So, first step of brown ring test is this. Now, secondly, the NO that is formed here, right, will react with Fe2 plus and will give you a brown complex. Now, this chemical composition of this brown complex you have to remember, this is very important. This is very important. Fe with 5 molecules of water and 1 NO as a ligand, right. So, this is responsible for the formation of the brown ring, right. Now, how this test is carried? The test is usually carried out by adding dilute ferrous sulphate, that is FeSO4 solution, to an aqueous solution of containing nitrate ion. Basically, you can take nitric acid also, right. And then carefully adding concentrated sulfuric acid along the sides of the test tube. For example, let us say this is the test tube here. You will add FeSO4 here. You will take a solution of FeSO4 here and you will take an aqueous solution of nitrate also into it. Now, you will pour the H2SO4 along the sides of the test tube here. You will not pour it directly, you will pour it along the sides of the test tube. Then you will see such a brown layer complex. This is known as the brown ring test. Okay. Now, applications of nitric acid. The major use of nitric acid is in the manufacture of ammonium nitrate, that is NH4NO3, which is used as a fertilizer, right. And other nitrates are used for the explosives or the pyrotechnics. and it is also used for the preparation of nitroglycerine, trinitrotoluene and other organic nitro compounds. Other major uses are in the pickling of stainless steel. So what is pickling of stainless steel? Basically, you know, you remove the amount of chromium content in the stainless steel, right? And etching of metals, if you see, basically making design on the metals, making some particular designs of the metals, nitric acid is used, and it is also used as a oxidizer in rocket fuels, and it is a good oxidizing agent. Preparation, if you see that barium NO2 hold twice with the H2SO4, it will give you barium sulphate as precipitate and HNO2 will be formed. So this is the preparation of nitrous acid. We are done with HNO3, we will be doing HNO2 now. Or NaNO2 plus H2SO4 will give you Na2SO4 plus HNO2. N2O3 plus H2 will give you HNO2. Ammonia plus peroxide will give you HNO2 plus water. So this is how basically you can prepare HNO2, that is nitrous acid. What is the oxidation state of nitrogen here? Plus 1 plus X minus 4. That means X equals to 3. That means the oxidation state of nitrous acid here is, the oxidation state of nitrogen in nitrous acid is plus 3. Now it is very unstable because it decomposes. So HNO2 basically decomposes to NO and HNO3. So here if you see, the oxidation state was plus 3. Here if you see, the oxidation state is plus 2. Here if you see, the oxidation state is plus 5. So can you see that it is a disproportionate reaction, right? The same species is being oxidized and the same species is being reduced. Here plus 3 to plus 5 it is getting oxidized, and here plus 3 to plus 2 it is getting reduced, right? And by the action of heat, HNO2 decomposes into H2O plus N2O3, which further decomposes into NO2 and NO. Okay. Now this is very important, that HNO2, because its oxidation state is what, basically plus 3, right? So it can go to the oxidation state of plus 5 also and to the lower oxidation state also, right? Like plus 2 or plus 1 basically. So it can act as both reducing agent also and oxidizing agent also, right? When it will act as a reducing agent, it will oxidize itself to plus 5. When it will act as a reducing agent, it will, when it will act as an oxidizing agent, it will reduce itself to plus 3 to plus 2. Okay. So here if you see, HNO2 is forming basically NO. That means plus 3 is being converted into plus 2. This means that it is being reduced, then it will act as an oxidizing agent. Now here reducing nature, if you see, HNO2, here it is plus 3, here it is plus 5. It itself is getting oxidized and will reduce the other species, right? So here you can see that HNO2 is giving 2 electrons. That means it is oxidizing itself. So reaction with ammonia, if you see, ammonia plus HNO2 will give you NH4NO2, that is ammonium ion with the NO2 group, and which further decomposes to nitrogen gas plus 2H2O. Now this is very important from organic chemistry point of view, formation of diazonium compounds, right? If you have done the haloalkanes or haloarenes chapter, basically what is happening here, that if you take aniline and treat it with NaNO2 plus HCl, NaNO2 plus HCl, which is basically what, HNO2, right? So if you treat it with this, you will get what, N2 plus Cl negative, N2 plus Cl negative. This is known as what, the diazonium salt. Okay. So if you treat aniline with NaNO2 plus HCl or basically HNO2, you will get what, diazonium salt. Now the question is, iodine reacts with conc HNO3 to form an oxo acid. So we have already done this, that iodine is converted into what, basically HiO3. So the answer for this particular question is B, HiO3. Now oxo acids of phosphorus we have to do. See, in oxo acid of phosphorus, the phosphorus is tetrahedrally surrounded by other atoms, right? That means it is having a tetrahedral geometry. All these acids will contain at least one P double bond O and one POH bond. The oxo acids in which phosphorus had lower oxidation state, means less than 5 basically, in addition to P double bond O and POH bond, they will also be having PP bonds or PH bond basically, right? We will do it in the next slides basically, that what is the structure of different oxo acids of phosphorus. Now this points are very important. The acids which contain pH bond have strong reducing properties. That means the oxo acids of phosphorus, the more amount of pH bond they are having, for example 1, 2, 3, when the number of pH bond increases, that means the reducing properties basically increases, right? Now see, these pH bonds are not ionizable to give H plus, and they do not play any role in basicity. This is very important, right? So for example, if you see POH bond, so H plus will be released where there is connection between the oxygen and hydrogen. It will form PO negative plus H plus. But if you are having a pH bond, basically P negative plus H plus is not there, right? The pH bond is only responsible for the reducing properties, while for the basicity POH bond is responsible. Okay. Now here if you see H3PO3, it is known as the orthophosphorus acid, right? Now if you remove two molecules of water through it, basically if you take two molecules of H3PO3 and remove one molecule of water through it, you will get pyrophosphorus acid, that is H4P2O5. And if you subtract basically one oxygen from H3PO3, you will get phosphenic acid, or it is also known as hypophosphorous acid, right? So here the oxidation state of phosphorus in phosphenic acid is +1. Here the oxidation state of phosphorus in orthophosphorus acid is +3. Here the oxidation state of pyrophosphorus acid is +3. Now we will determine the basicity basically. Here 1 OH bond, so basicity equals to 1, that means monobasic. 2 OH bonds, that means basicity is equal to 2, that means dibasic. Here 2, that means it is dibasic. 2 OH bond, that means dibasic. Okay. Now H3PO4, if you consider, that is known as orthophosphoric acid. Now you take two molecules of orthophosphoric acid and remove one water molecule through it, you will get pyrophosphorus acid, which is tetrabasic. How it is tetrabasic? See, 1, 2, 3, 4. So 4 OH bonds are present, that means it is tetrabasic. Now if you remove one water molecule from orthophosphoric acid, you will get metaphosphoric acid, that is HPO3, where the oxidation state of phosphorus is basically +5, and it is monobasic. Why? Because it is containing only one OH bond. Now here if you see the H3PO4, that is the orthophosphoric acid, it is containing 1, 2, 3 OH bond, that means it is tribasic, right? Now from pyrophosphorus acid, basically if you remove one oxygen, that will give you hypophosphoric acid, which is tetrabasic. 1, 2, 3, 4. So it is tetrabasic. Now can you see here that this particular oxygen is being removed and a PP bond is being formed here. So this you need to remember. Meta is used for acid obtained by loss of one water molecule. So here if you see that this is the parent acid, that is the H3PO4 orthophosphoric acid. If you remove one water molecule, you will lead to metaphosphoric acid. Pyro is obtained when two molecules of the parent acid are taken and water is removed from it, right? So here if you take two molecules of orthophosphoric acid and remove one water molecule, you will get pyrophosphorus acid. Hypo is obtained when you remove one oxygen from the pyrophosphorus acid. So one oxygen is removed here, so it will give you hypophosphorus acid. So these are very important, right? These structures, basically the questions area comes under this, that what is the number of P double bond O, POH bond, PH bond, PP bond in different oxo acids of phosphorus. So these are the question areas basically. So hypophosphorus acid H3PO2. So remember that hydrogen, maximum amount of hydrogen will be placed with the oxygen only, right? So here if you see one double bond O is always there. Now draw one oxygen, hydrogen will be present next to it. Now since there are no oxygen, two oxygens were there only. So now you will make the pH bonds, right? So the oxidation state of phosphorus is basically +1. So it is having one POH bond, two pH bond and one P double bond O. So its preparation can be done with white phosphorus when you treat it with the alkali, basically KOH or NaOH basically. So you can lead to the formation of the hypophosphorous acid. Next you come on to orthophosphorus acid, that is also known as the phosphonic acid, H3PO3. Now first drop P, double bond O, oxygen, oxygen. Now place hydrogen here, one hydrogen here, two hydrogen here. So 3 oxygens are completed, but there are 3 hydrogens. So make one pH bond here, right, as there are no hydrogens left. Oxidation state of phosphorus is +3. How many POH bonds are there? 2 POH bonds are there. One P double bond O is there and one pH bond is there, right? So the preparation is by treating with P2O3 plus water, you can get H3PO3. Next, coming on to the pyrophosphorus acid, that is H4P2O5. So oxidation state of phosphorus is +3. Let us draw the structure now. See here, try to draw the symmetrical structure basically, right? So here if you see phosphorus, phosphorus. Now here if you see no double bond O is present, right? So OH here, OH here, OH here, OH here. Now one oxygen is left, right? So you place it between. When you are drawing the structures, try to make the structure symmetrical basically, right? So here if you see 2 POH bonds, just a second. Yeah, total if you see 1, 2, 3, 4 POH bonds, 1 POP bond, that is very important, 1 POP bond. And the preparation is basically PCl3 plus H2PO3 will give you pyrophosphorus acid. Now hypophosphoric acid, that is H4P2O6. So the oxidation state of phosphorus here is +4 basically, right? So here if you see, draw the structure phosphorus, phosphorus, place double bond O here also, place double bond O here also. Now there are 6 oxygens that need to be symmetrically distributed between the 2 phosphorus, right? 2 are done. So let us say 1 oxygen here, then again 1 oxygen here. How many are left? 1, 2, 3, 4. 5th and 6th, right? Now place the hydrogens 1, 2, 3, 4, right? So and hydrogens are also completed, 1, 2, 3, 4. Oxygens are also completed, 1, 2, 3, 4, 5, 6. So make a PP bond here, PP bond here. Okay, so 4 POH bond, 2 P double bond O and 1 PP bond. Now this is very important. See, if you take one phosphorus on single phosphorus, 2 OH groups if you see, basically they convert into P double bond O, right? They try to convert into P double bond O because P double bond O is very stable as compared to that of 2 POH bonds, right? This you must be doing in the chemical bonding also, that phosphorus has a great affinity for oxygen. P double bond O is very stronger. So basically 2 OH groups if are there, it tries to its maximum limit that these 2 OH are converted into double bond O. So that was for general knowledge. Now we come on to the preparation of hypophosphoric acid, that is red phosphorus plus alkali, that is NOH or basically KOH. Orthophosphoric acid, if you see, it is H3PO4. How will you draw the structure? P double bond O, 1, 2, 3 and place hydrogens, right? So oxidation state of phosphorus is +5, 3 POH bond and 1 P double bond O, and it is prepared by P4O2N plus water will give you what? Orthophosphoric acid, that is H3PO4. Pyrophosphoric acid, if you see, H4P2O7. Now draw the structure P, double bond O is present. Symmetrically distribute the oxygen. 1 oxygen here, 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 1 oxygen here. So 1, 2, 3, 4, 5, 6. Now the 7th oxygen will come in between. Okay, and hydrogen here. Okay, so the oxidation state of phosphorus is +5 basically. How many POH bonds are there? 1, 2, 3, 4. 2 P double bond O are there and 1 POP bond is there, right? So if you heat phosphoric acid, basically you will get pyrophosphoric acid, that is removal of water basically, right. Now here if you see metaphosphoric acid, this is very important. It exists in polymeric forms only. It exists as a polymer where the monomer is HPO3. So here you can see that it is cyclotrimethaphosphoric acid HPO3, that it is the trimer of metaphosphoric acid. Here if you see polymetaphosphoric acid, now this chain will continue from this end also and from this end also. So here if you see the structure, basically 3 POH bonds. See here, let us take this unit. 3 POH bonds, POH, 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 and 3 P double bond O, P double bond O, P double bond O, P double bond O, 1 OH here, 1 OH here, 1 OH here, and 3 POP. 1 POP, second POP, right? Or let us see the cyclotrimethaphosphoric structure basically, because here the chain is not completed. See here, 1, 2, 3 POH bonds, 1, 2, 3 P double bond O, 1, 2, 3 POP, right. So its preparation is phosphorus acid plus bromine. When it is heated in a sealed tube, you will get the metaphosphoric acid. So basically there are two polymeric forms, metaphosphoric acid and polymetaphosphoric acid, right. So while determining the number of POH, P double bond O and POP, basically consider the cyclotrimethaphosphoric acid, right. You will get confused if you will take the polymetaphosphoric acid, because you have to complete the chain then, right. So yeah, oxo acids we are done. Now basicity comparisons. Now here if you see H3PO3 and H3PO4, if you draw the structures here, it is having 2 OH groups, so it is dibasic. If you H3PO4 is having 3 OH groups, so it is tribasic in nature. Disproportionation reaction. What is disproportionation? That the same species is getting oxidized and the same species is getting reduced, right. So acids which are in +3 oxidation state of phosphorus tend to disproportionate to higher and lower oxidation state. If you see here, let us say +3 plus X minus 6, that means the oxidation state of phosphorus will get out to be +3. Now here if you see +3 plus X minus 8, here the oxidation state of phosphorus is +5. Here if you see the oxidation state of phosphorus is basically -3. Right. So can you see here that +3 to +5 it is getting oxidized, and +3 to -3 it is getting reduced. So H3PO3 basically disproportionates to H3PO4 plus phosphine. Reducing power. Now this is very important. The acids the oxo acids basically which are containing the more number of pH bond will be more reducing in nature, right. So here if you see the structure of H3PO2, it is containing 2 pH bonds, so it is a good reducing agent, right. Now here see, this reaction is very important, right. How it is acting as a reducing agent basically. Here if you see, it is H3PO2, right. If you draw the structure of H3PO2, this is this. Now draw the structure of H3PO4 as it is being converted into H3PO4. Draw the structure of H3PO4. It will be P double bond O, OH, OH and OH. Now can you see here that the two pH bonds are converted into POH bond. Now this pH bond were giving -1 oxidation state. Each pH bond was giving -1 oxidation state to phosphorus, right. Now here if you see, the two OH bonds are giving +1 oxidation state to phosphorus itself. Each POH bond is giving +1 oxidation state. So this is how basically it is having a reducing property. Here if you see, the oxidation state will come out to be how much? +3 plus X minus 4. That means X equals to basically +1 here, right. Here if you see the oxidation state, it will be +3 plus X minus 8. So oxidation state is here +5. That means it is oxidizing itself and reducing silver. Ag is in +1 oxidation state here and Ag is in 0 oxidation state here, right. So this reaction is very important, that how basically pH bonds are acting as a reducing agent, that they are converting itself into POH bond, and due to the POH bond, each POH bond gives +1 oxidation state to phosphorus, while each pH bond gives -1 oxidation state to phosphorus. Which of the following has more reducing power and why? Hypophosphorous acid, orthophosphorus acid and orthophosphoric acid. So see here, the names are very important. The names of the oxo acids, you have to remember it by heart, right? They will not give you the chemical formula, let us say H3PO2, H3PO4. Instead, they will give you their names: orthophosphorus acid, hypophosphorus acid, orthophosphoric acid, right? So remember the names of the oxo acids and also the structures. So here if you see, H3PO2, H3PO3 and H3PO4, right? It is asking that which one has more reducing power. So here if you see in H3PO2, 2 pH bonds are there. In H3PO3, 1 pH bond is there, and H3PO4, no pH bond is there, right? So this will be more reducing in nature. That means it will act as a reducing agent. It will oxidize itself. Which of the following is a cyclic oxo acid? That we have already done. Which of the, that HPO3 basically, HPO3 is a cyclic oxo acid. We had done the trimer basically, so it will be H3P3O9. So cyclotrimetaphosphoric acid, HPO3. Okay. Now come on to the fertilizers basically. See, this is not mentioned in NCERT, right? So pay attention to these. You don't have to remember the chemical reactions. And also, yeah, one thing important, the oxo acids reactions, they have not been asked in the exam, yet you are having the reactions basically of oxo acids in your material that is given by concept tree, right? So you can just have a look at them. And fertilizers, it is not given in NCERT, so pay attention to this. See, what are fertilizers basically? They are the chemical substances which are added to soil so that, let us say that some deficiency of nutrients is there by plants, right? So that deficiency of nutrients is made up by the fertilizers. So nutrients are classified as primary nutrients, secondary nutrients and micronutrients. So primary nutrients, if you see, which are consumed in large quantities, that means nitrogen if you see, phosphorus if you see, and secondary nutrients if you see, they are calcium, magnesium. Micronutrients if you see, which are required in minute quantities basically, for example copper, zinc, manganese, boron, chlorine, iron are required in minute quantities by the plants itself. Okay. Now the types of fertilizers, if you see, nitrogenous, phosphatic, potash and mixed fertilizers. So we will information about each type of fertilizers one by one. First is the nitrogenous fertilizers which supply nitrogen basically, right? So here if you consider urea, ammonia plus carbon dioxide will give you what? NH2CO, NH4. Now this will decompose into urea, that is NH2CO, NH2, which contains 47% of nitrogen. So ammonium sulphate can be prepared by ammonia plus water will give you ammonium hydroxide, which on reaction with carbon dioxide will give you ammonium carbonate, which reacts with calcium sulphate to give ammonium sulphate, which acts as a sindri fertilizer. Basic calcium nitrate, which is also known as nitrate of lime or Norwegian saltpeter, right? So here if you treat calcium carbonate with nitric acid, it will give you calcium nitrate. This calcium nitrate on reaction with calcium oxide will give you the basic calcium nitrate, right, which acts as a fertilizer. Calcium, that is CaCN2, you can prepare the calcium cyanamide. Actions are not important, you can remember the names of the fertilizers itself. And more about fertilizer, I guess you are having in the environmental chemistry or chemistry in everyday life, I guess, right? So more about fertilizer you will learn there. Phosphatic fertilizers, if you see, superphosphate of lime, right? So calcium phosphate on treatment with H2SO4 will give you superphosphate of lime. You can remember the chemical formula. So available phosphorus is 16 to 18%. Just a second. superphosphate of lime, if you see, calcium phosphate plus H2SO4 will give you superphosphate of lime, and the available amount of phosphorus is 16 to 18%, right. Now next is the phosphatic slag or Thomas slag basically. So when you treat phosphorus with oxygen, you will get P4O10, which on reaction with calcium oxide will give you calcium phosphate, right. So it is basically the byproduct of steel industry, and the available amount of phosphorus is basically 14 to 18%, right. Again I am repeating, you need not remember the reactions, you can remember the chemical formulas itself, okay. Next is the triple superphosphate, that is on reaction of calcium phosphate with phosphoric acid basically, and calcium H2PO4 whole twice. So this particular, the mixture of these three is known as what? The triple superphosphate. Next are the potash and the mixed fertilizers basically. So for potash fertilizers, these provide potassium to the plants, right? Example KCl, KNO3, K2SO4, these are the potash fertilizer. Mixed fertilizers, if you see, ammoniated superphosphate, so it is prepared by spraying ammoniation solution, that is ammonium nitrate 65%, ammonia 21% and water 13.27% on superphosphate. That is known as ammoniated superphosphate. So they are basically mixed fertilizers, right? Potash fertilizers will impart potassium to the plants. Nitrogen fertilizers will impart nitrogen to the plants, and for mixed fertilizers, if you see, they are mixed compounds that can be supplied to the plants. Okay, so that's all for today. Anyone wants to ask some sort of question? Anyone wants to ask some sort of question? You can ask. So that's all for today. Thank you.